So first off, MassHunter has three main features: acquisition, quantitative analysis, and qualitative analysis, all of which utilize a common reporting engine with Excel and or PDF templates available. And something to mention at this point as well is that our templates are not password protected. So you can go in and using MassHunter Report Builder, edit and configure your own template to your specific needs. Also, if a template does not meet your specific requirements for your application, Agilent can customize reporting templates for you. However, I would mention that if you are going to edit a reporting template that comes with the system, that you make copies before you start doing your editing. So some of the applications and features within the MassHunter software suite that fall either under acquisition, quant, or qual are things such as retention time locking, a method translation software which can convert ChemStation data into readable MassHunter data. Now, this is something that is reverse compatible and allows you to still utilize this data file in ChemStation or look at data in MassHunter data analysis. Also, the one that we're going to focus on mostly is the unknowns analysis, and this occurs in the quant software section of the software. Notice as you look down the list, there is not just features for single quad type data, but also for QTOF and triple quad data as well. This is because the MassHunter software suite can control LCMS and GCMS instruments, along with standalone GC and standalone LC with VWD detectors, DAD detectors. Again, it can be single quad, triple quad, QTOFs, and ICP-MS. So what this enables you to do as a customer in your laboratory is to be able to have all these different analytical techniques, but only have to understand and be an expert on one software system, which really does make things more efficient. Now, again, I did mention that the software does have translational macros built in to be able to do ChemStation data translation so that MassHunter can look at old ChemStation data. So you don't have to worry about once you move to MassHunter not being able to look at old ChemStation data. In fact, it's reverse compatible. So once the data is translated, you can still utilize the data file in ChemStation data analysis. We're also able to, in MassHunter translation software, to migrate or translate a ChemStation quant method and move your compounds, your calibration levels, your retention times, your qualifier ions or your sim ions, and move them into a MassHunter quantitative method. And that translation software is available, again, also in the MassHunter software suite. Depending upon how close you've paid attention as the different software versions have been evolving through Agilent, you may not have ever noticed that there was a migration from MSD Productivity ChemStation acquisition to MassHunter acquisition, because they utilized a lot of the same icons and workflow that was part of the ChemStation program in MassHunter acquisition. So the overall workflow is the same. One of the things that I try to point out when talking about MassHunter and the different components in MassHunter is that there's a lot of overlap in qualitative and quantitative analysis. So in other words, you can do targeted deconvolution in qual, and you can do deconvolution in quant as well, and in unknowns analysis. You can do multi-library searching in qual. You can do library editing and searching in quant analysis. So there's a lot of different functions that are available in both, and it really just depends upon your workflow and what you need to get out of your data as to which, if not both, of the features of software you utilize and which best fits your overall workflow. One of the nice things about MassHunter in qualitative analysis is the use of the NIST MS program search. And so it transparently links to the NIST MS search program in qualitative analysis and can search that NIST database, giving you head-to-tail comparisons, searching by name, searching by molecular weight or CAS number, all the different features that are available to you in the NIST MS program search. One of the things that it also does is give you the ability to utilize your .L library. So if you have specific libraries that you're currently using in ChemStation, it allows you to use that .L library as well as create your own in-house libraries. And so this is just a very short list of a lot of the different libraries that are available to you from either Agilent or outside sources that meet that .L format. Next, let's go specifically into unknowns analysis, which again is found under the quantitative analysis umbrella of MassHunter. And let's go through the specific workflow process. Just as in ChemStation data analysis, there's a workflow for unknowns analysis. And the first step in that workflow is creating a batch. Now, a batch is basically a file, a directory, where you're going to place the samples of interest that you want to analyze. Now, these samples can be case samples, they could be standards, they could be blanks, they could be continuing calibration files, they can be matrix blanks, spikes, all kinds of things. Anything that you can generate on your system can go into a batch. One of the key features, however, is that when you create a batch, you normally want to create it in the directory where your data files are located. That doesn't preclude you from importing data files from other directories, but it does make it less confusing when you want to go back and look at the unknowns analysis batch and where those data files are located. Now, when you create a batch, you're going to, just as in ChemStation, create a data analysis method specifically for that batch. And you can load different unknowns data analysis methods in a batch and reintegrate, re-extract, re-deconvolute, re-integrate, all the different parameters, library searching, and things you can do multiple ways and multiple times within a batch. Some of those things that you can do are things such as tick analysis, which is basically peak integration. You can also run deconvolution. Both of these tasks will create components or integration peaks, and it will also perform library matching on those peaks. And then you can manually go through during your data review process, look at the different peaks, look at if you have any co-eluding peaks, look at the library matches, manually research a library if you'd like. And in the process, we will show you how to manually generate a component and manually integrate in unknowns analysis as well. Before we bring up unknowns analysis, I want to let you know there are multiple ways of bringing it up on your system. You can go to the Start menu and look under the Quant folder for unknowns analysis. And depending upon how your system is configured, from your desktop, you may see these two different icons, one Unknowns My Way and Unknowns Analysis. These are both going to take you to unknowns analysis, but they're presented in a different format depending upon how your system is configured. So what's on the screen currently is Unknowns My Way. For those of you that may be familiar with an Open Lab format, this is placed into an Open Lab format to where you have various tabs to access the different features and functions within unknowns analysis. Now, the other format is what I call a classical format, which this is unknowns analysis in a classical format, which is the format that I'm going to be teaching. However, the functions are the same. It's just presented and displayed differently. So we're going to be specifically working in the unknowns analysis classical format with the menu bars up here and the drop-down menus, as opposed to the various tabs that are available in the OpenLab format. So to begin the discussion of deconvolution, basically a little historical background. Deconvolution is something that is not new. It's been around for decades. In fact, the first deconvolution algorithm was started up by NIST, and they started a deconvolution algorithm called AMDISC, which is Automatic Mass Spectral Deconvolution and Identification Software, as you see up on the screen. And again, this was initially developed for chemical weapons and for chemical weapons analysis, looking for co-eluding peaks and low-level responses of different byproducts and parent products in the chemical weapons arena, and has been applicable to other areas, including forensics, utilizing retention time, deconvoluted spectra, cleaned up spectra where background has been removed to get a more clarifying spectral match and response, and has pretty much been used all over the world. In this instance, we're going to be using Agilent's deconvolution algorithm, but again, works very similar but is different from the NIST algorithm. So under this basic theory, you have a peak, as you see up on the screen, that may look fairly Gaussian, and sometimes they may have shoulders or splits, kind of giving away that there may be multiple components under the screen. Well, in this instance, our Gaussian peak looks like it has one component underneath it, and as we go and walk the chromatogram or move our cursor, as we're doing in data analysis ChemStation, and looking at the different spectral features of our peak, we notice that as we're going up our peak, our spectra is of a certain type or compound. And then as we get further along, we notice our spectra changes. And as we go down the backside of our peak, we see a different spectra. And then, like I said, in the middle, we're seeing even another spectra. So usually what you're going to be stuck doing is trying to do a background subtraction on the front, but then you're still remaining in that spectral table ions from the impurity that may be on the backside of the peak, and those of our possible analyte or compound of interest. So they're going to be all overlapping depending upon the area, specific area, that you take your spectral reading from. So what deconvolution does is based upon an extracted ion chromatogram where it lines up and generates a spectra table based on ions that have been extracted with the same retention time and compound peak shape. It will place those into a bucket to generate a spectra. And so as the deconvolution algorithm is going across that, what we think is a one peak, it's pulling out extracted ions and placing them with the same retention time and peak shape features into a spectral table. And it does that as it goes through that ion peak, creating that spectral table. And then as it goes across the peak, it happens to actually see that compound of interest that we're wanting to report, and generating a spectra from it. And as you can see, if you just did the apex of the peak, this is the type of spectra you would get. You're going to get interferences from the first component, the second component, and the compound of interest, or our target component. And so again, if you're trying to do background subtraction on the front side or back side of the peak, you're always going to be missing and looking at merged spectra from another impurity that may be coming out in that peak. And so deconvolution helps to separate and bring all of this out. And then as it identifies these different components that make up this one peak, generating the spectral table and then going and searching that spectral table against our library of choice, whether it's an in-house library or whether it's a commercial library, searching it out. So again, I mentioned previously that deconvolution is available in qualitative analysis. It's available in unknowns analysis and is also available in quant by itself. But what we're going to focus on specifically in these next two videos is unknowns analysis and how to develop a workflow and a data analysis method in unknowns analysis. One of the other features that's worth mentioning in unknowns analysis, besides deconvolution and peak analysis integration, is the ability for unknowns analysis to utilize retention time and retention indices as an additional level of confidence when reporting your spectral library matches of the compounds of interest or your target compounds. And so what you see on the screen is a unknowns analysis component table listed with various drugs. When I generated this library, I carried over with the spectral entry the retention time entry as well. On top of that, I generated a retention indices file based on N-alkanes from C7 to C36, which in turn in the software generates a component retention indices. Now, what allows me to do this is as I'm doing my data analysis method, I can include these parameters in my data analysis method, which is going to report the difference in retention time and or the differences in retention indices, and therefore giving me an additional level of confidence in not just my spectral match, but also my retention or my elution match with that specific compound. Another nice feature in this is that depending upon the libraries that I'm using, in this instance, I used an in-house library that I generated. I could also use a NIST library like NIST 17 or NIST 20. And in those libraries, a lot of their entries have retention indices assigned to those different components, to those different library entries based on their midpolar columns. And depending upon where the best library hit is, it will import the retention indices for that specific library entry into my table as well for comparison purposes. So it really does have a lot of horsepower besides just the deconvolution or cleaning up of spectral software or overlaps of spectral tables in the chromatogram, but also bringing into it additional identifying factors such as retention time and retention indices. And so again, that accurate retention time can really help give an additional level of confidence based on the compounds that you're looking for with the extracted ions being present and their retention times. This is kind of a real life example of what deconvolution can do. What you see in the top tick is a conventional chromatographic separation of 12 fentanyl analogs. You're only seeing 11 of the fentanyl analogs because the other one is out here at about 23 minutes. It's phenoxyacetylfentanyl, which comes out at about 23 minutes on this column. This is a 25-meter column, 0.2 by 0.33 dB5, I believe. And I get really good separation on most of the 150 or so fentanyl analogs. In fact, in what you're seeing in this top tick is the separation of methacrylfentanyl, 3-methylfentanyl, and alpha-methylfentanyl. And then these last two between 15 and 16 minutes is cyclopropylfentanyl and cropylfentanyl. Okay, so kind of keep that in mind. We've got separation and specific retention times in this 25-minute run. Well, on the bottom chromatogram, this was actually generated with a quick probe, one of our screening techniques that we have on our GC mass spec system for single quads. And this analysis took place in a little under a minute. And you can see that where we had our 3 fentanyl analogs that we had baseline separation here, we've got coelution here. And in the last 2 cyclopropyl and crotonal fentanyls, we've got coelution as well into one peak. But we have separation of our early eluting fentanyl analogs and our mid eluting fentanyl analogs as well. So it's just in these last 2 that were being zoomed in on do we have kind of a coelution effect. So this is going to give you a good example of what deconvolution can do for you when you compare it to peak integration. And peak integration generates a components list. It's integrating. It's an algorithm in itself. It's integrating just as it is in ChemStation, telling you where peak baselines start and stop and identifying it as a peak by assigning it a retention time and then doing a library search based on the libraries that I used. And in this instance, it was NIST Library 20, and it was an in-house library of fentanyl analogs that I utilized. And you can see that on the coeluting fentanyl analogs, it called the peak a 3-methylfentanyl analog. And it didn't have a great response as far as a library match factor, about 73, but all the others, good library matches in the 90s and 80s. And it called the cyclopropyl and crotonal fentanyl as far as a spectral match. After running deconvolution, you can see that deconvolution algorithm actually said, there's not just 3-methylfentanyl in here, but there's also in the beginning of this peak, the methacryl fentanyl. And in the middle of the peak, the 3-methylfentanyl, and then at the backside of the peak, the alpha-methylfentanyl. And these gave actually pretty good library matches, and not just with an in-house library, but also with NIST as far as the quality match in the 80s. Now, let's look also at this crotonal fentanyl. If we go and look at it, it called it crotonal fentanyl, even though we know it consists of cyclopropyl and crotonal. Well, for those of you that are familiar with it, one of the things, if you'll look at the deconvoluted spectra and the library spectra, we have a good match. But if you go down into what is considered the raw spectra, it pretty much is the same thing. And because of that, it's because the cyclopropyl and the crotonal fentanyl are isobaric. They basically have the same molecular weight and generate, in this instance, the same spectral pattern. And so you need, when trying to determine whether you've got cyclopropyl or crotonal fentanyl, you need the ability to be able to separate these 2 compounds chromatographically. So this kind of summarizes what we have in deconvolution, and I hope this helps you in understanding as we go into the software now to discuss and load data and go through the workflow process of integrating and library searching our unknown samples. Look forward to seeing you in the software section. Okay, I hope you found the PowerPoint presentation informative. And what we're going to do now is spend the rest of the time of this video in the software itself. However, to make things easier for you to follow me, like I said, I'm going to be working in unknowns analysis classical mode. And we also have unknowns analysis my way, and which is more in an open lab format. So what I want to do real quick is show you how to change it to the classical or even the open lab if that's what you prefer. So real quickly, what we're going to do is go into the file manager view, and most of you, your software is going to be on your D drive. on my instance, on my laptop, it's on my C drive. So what you're going to want to do first is go in and click on Program Files. From Program Files, you're going to go to the Agilent directory. From the Agilent directory to MassHunter, Workstation, and then Unknowns Analysis, if you remember from the PowerPoint presentation, resides in the Quant software. So we're going to go into Quant, and we're going to go into Bin. And from the bin, you're going to scroll down and look for the Setup Desktop Icons WPF application. Now, there is a .exe file, which you do not want to run. You want to run the application. And the easiest way to do this is to click on it and then right-click on it and send it to your desktop as a shortcut. And so we're going to do that. And let's see where it went as far as on a shortcut. I'm going to minimize my screen. Of course, I have multiple monitors going on right now, and I don't see it. So let's see where it is. Okay, I've ended up all the way 2 monitors over. So let me bring this over. And this is what the desktop looks like. You can see that I have 2 of them, and this is the first one that I have, that I created, that I use frequently to go and create the different icons. Now, if you bring this shortcut up, it will ask you, can't see it on my screen, but it'll ask you, is it okay to take charge of your this app to be able to make changes to your device, which you click yes. And then what it ends up doing is bringing up this window, which you'll want to put in the, instead of Quant My Way tab, go to the Classical UI tab and put in that you want a single quad or for a triple or for whatever you're trying to configure. Highlight in the Classic UI tab the MS single quadruple, put a check mark there, check mark on unknowns, click on apply, then OK, and it will create the icons for you. If you want the Quant My Way, just click on that tab, click on what instrument configuration you want to use, and whether you also want a vanilla configuration, which we won't go into right now, but the Quant My Way configuration, click on apply, click OK, and it will create the icons that you see here that are more in the Open Lab format or the classical UI format. So that's how you can change the format on your system. And I didn't spend a lot of time on that, but that's because you can go back and replay the video and do it a little bit at a time for you to create it. So once you have the icons on your screen, you can go and left double click on the Unknowns Analysis icon, and it's going to start up. Give it a few minutes. We're going to make it full screen. Now, hopefully your Unknowns Analysis looks very similar to my screen. One of the things that you may notice will be different are that my fonts are bigger. I do that on purpose so that people can see the information on the screen. My mouse or my cursor icon is bigger and it's black. And again, I do that to be able to show where it's going and hopefully to help you follow my mouse strokes as I go through the system. So we have Unknowns Analysis brought up on the screen. And now what we want to do is load the eval demo. Remember, I mentioned that in the PowerPoint presentation. So the next thing is let's go and find the demo file so that we know what directory it's in. First, before we do that, on our way to do that, let's create a new batch. Now remember from the PowerPoint presentation, the batch can consist of any type of data file, whether it's a blank, a sample, a standard, continuing cal, matrix spike, any kind of sample that you can think of can go into your batch. And we normally want to create our batch where our data files are located. In regard to that, we can bring other files that aren't in that directory into our batch. But again, it just makes life a lot easier. We're not hunting and pecking for data if we can keep our batch file with the directory of our data file. Okay, so let's create a new batch in unknowns analysis. And so we're going to go to File, left click, New Analysis. It's going to take you probably, if unknowns has opened before, to an area or a directory that you may have used last, but we're going to start from this PC. The data file on most configured systems with MassHunter would be on the D, as in David drive. Mine is on the C drive. So you're going to replace C drive with the D drive. We're going to go to MassHunter directory. Under MassHunter is the data directory. We're going to click on the data directory, and that is where the eval-demo.d file should be located. If yours, for some reason, is not there, I would try to do a search on your computer to find the eval-demo.d. So where it's located is where we're going to create our new batch. And so I'm going to call this training 2. And create it. Now that I've created it, I'm going to load a sample into the batch file. And so I'm going to go back to File, go to Add Samples. And because I have multiple samples present, I'm going to just click on the eval demo. But it automatically highlights the number of samples that are present in that directory, and we can pick and choose which samples we want to add to the batch. And remember, I stated earlier, you could go to Browse and bring in other samples from other directories that you may have reviewed in the past. So there is a way to do that, and we'll go into that in a few minutes. So we're going to load the eval demo sample, and when we do, it comes up on the screen. File. Very simple data file, not complicated or anything at all. It has 4 compounds in it and a very quiet baseline, very little noise of any consequence in the baseline whatsoever. If you notice, if I put my cursor into my x-axis, you can see I get a double-sided arrows. I got double arrows on it. What that means is it's my cursor has gone into a different mode. If I left click and hold my mouse button down, it locks the x-axis and moves the x-axis around. If I do the same thing and right click and hold down my mouse button, I can actually change and expand or shorten the x-axis. Go ahead and do the same thing in the y-axis. Left click and hold, sets the y-axis and holds it, or I can get my double arrows, right click and hold, and actually expand or shorten my y-axis. So it makes it very nice. One other feature is, let's go over here. I'm going to bring back in my x-axis a little bit to get all my peaks back in. And you can see I've got a peak here that may be of something significant. I can take my cursor, right click, and hold it down and drag, and you can see it turns into a magnifying glass, and I'm zooming in. If I let go, it zooms in. I can increase my y-axis, bring it down, increase my y-axis with my right click, bring the baseline down with the left click, and if I wanted to, I could come to my x-axis and right click and pull it in, sharpen my peak up. You can see that's my other peak coming in. Again, x-axis with the left click, locking it and moving it more into the center of my screen. Okay, if I want to go back, one of the big things in MassHunter is called the right click menu. What this enables you to do is right click with your cursor in the tick box, and you'll see there's a right click menu with different options. If I wanted to do a previous zoom, I could click here. If I wanted to go back to an auto scale, I can click here. And that's what I'll do. And it brings me back to the auto scale. So really nice to be able to move your scaling around so that you can look at your tick how you want to look at it. You can set this window layout any way that you're comfortable with. If you come up to the view window, you can see there are preset layouts, which is the standard layout, which is what I am in. There are extended, condensed, all different types of layouts. And let's say you're using the same system and you have another analyst and they like looking at a different layout. You can load your layout that you like, save it, and then when you come back onto the system in the future to look at your data, you can load your layout. So it really is very flexible on how you want to do things. The other thing that I want to point out is that you can move windows around. Again, going to that double arrow, I'm moving my cursor to the edge of the frame of the window. I'm left clicking and dragging, and so I can move them back and forth, left clicking and dragging to expose different levels of my tables on any window. And I'll be doing this during the training, is I will put my cursor and click on the menu bar, right click, and again, another right click menu pops up and it says hide or float. If I float it, it basically releases it. Of course, mine puts it on another screen, but I'm going to drag it back in here and it goes into the middle of the screen. And then I can show you different parts and I can resize it and all kinds of stuff. And so this is a nice way to get a picture of screen that you want to see. It's a nice way to do presentations so that you don't have to move everything around. And if I want to go back to where the original window was, I can right click in the title bar and take the checkbox off and it goes back where it was. So another thing I want to point out is that you're going to see a lot of drop down menus and items on the screen that I will not be going into. Due to time, I'm trying to keep this as succinct as possible for you to get the most out of it and to be able to use the software. You'll be able on your own time, once you get used to the software, to move around and explore the different areas. So if you see something that I don't go over, it's because at this point in time, it's not important for you using the software. So the next thing we're going to do is go in and develop our method, our data analysis method, specifically for this eval.d file. So let's go up to method, left click on our method, and go to edit. And our method edit window pops up with multiple tabs on it. Now, this peak detection tab is the first tab we're going to deal with, and by default, it starts out with deconvolution. Knowing that majority of you have probably not been using deconvolution, we're going to left click on the drop-down menu and go to tick analysis. Sure mass, you're not going to want to deal with. That's for accurate mass QTOF data, so we're not going to even talk about that today. And we're going to do tick analysis, which is basically peak integration. Now, you can specify if you have different scans or signals. So in other words, we have a tick signal, a total ion chromatogram. If you had GCs, you could also do retention time signal searching on this. Next area is a peak filter, where you can exclude masses that you don't want the system to look for. This is using, as an example, mass 28. Which, again, this is totally up to you. I don't recommend excluding masses. A lot of people say, well, what about excluding masses that are in column bleed and things like that, 207, 285. Well, I've seen those masses in regular spectra as well. I prefer not to exclude any masses, but that's totally up to you. I'm not scanning down to mass 28, so I'm not excluding it because I'm scanning at mass 40 and above. This is actually a very nice parameter to use, which is signal to noise ratio. And what this can do a lot of times, and you've got to run it at different times and see what works best for your samples and your matrix, but this can help limit the amount of components that the integration finds in your tick. You can set this based on your SOPs or your experience, but this is a good tool to use to minimize what the system sees, or in other cases, to maximize what the system sees. We're going to leave it at set 0. We're going to kind of skip the maximum number of peaks. We're not going to have anything there. We do have additional filters on this tab, just like you do in any integration where you can filter based on area or based on height. And we're not going to filter on anything. We can filter greater than or equal to and do a specific number of counts, or a relative area based on the largest peaks. And again, we're not going to do any of those parameters right now. We're going to skip the deconvolution tab because we're not doing deconvolution. We're doing tick analysis or peak integration. But what we do want to go to next is our library search tab. Now, by default, the library search tab goes to the demo library, which we want to go and change. On your system, it really depends on where your library is. My system remembers that it's on my C drive under the library directory. Probably under yours, it's under the D drive, and then library, and then the directory that you have. I have multiple libraries, as you can see on my system, and I'm going to use the NIST 20 library for right now. So I can just click on it and click open, or I can just double left click on it and it loads it. I can search multiple libraries. I'm not going to do that. I'm going to keep it simple and just search one library right now. I can also adjust the scoring, where if I want to adjust it to the NIST scoring algorithm, it will do that. It won't set it exactly to the NIST score, but it will get it closer to the NIST score if you're used to using the NIST algorithm. We're going to be using the Agilent library search algorithm. We can weight it, whether it's 70% or 30% of the spectra. And again, we're not going to change any of these on reverse or forward matching. We're going to leave it at the default of 0.7. You can remove duplicate hits. There's a lot of libraries that have multiple entries for the same compound. This just kind of helps to clean things up a little bit. We can check it or uncheck it. I'm going to leave it unchecked. And then in the PowerPoint presentation near the end, I mentioned using retention time as a match factor to help increase your level of confidence. If you wanted to use that, you would put a check here, and you can see these fields become highlighted. I'm not going to go into using retention time matching or creating a retention time calibration file. I actually do have a video out there under the Power of MS on our On24 website. And so if you would like to see that, I do go into detail on using retention time matching and a retention indices file for creating those indices. Okay, from here, let's move from the library search tab to the compound identification tab. Under this area, we're going to set how many hits we will have for a particular library match. Again, to kind of make this very simple, we're going to just show one library hit, depending upon the library that we're using. We're going to start out with a minimum match factor. Instead of 50, we're going to highlight it and put in 70. And just like signal to noise ratio, the minimum match factor is a good way to filter the data that you're doing analysis on. And so a minimum match factor of 70 is a good place to start. Minimum M over Z, our mass to charge, this should be able to read the data file now. I believe it's unknowns is smart enough to know what your scan range is, but on the earlier versions, this is version 10.1. On the earlier versions, I don't think it had that capability. So I like to just be sure and put in, since my scan range is 40 to 550, I'm going to go ahead and do a minimum scan range of starting at 40. What this means is that when I'm comparing to the library match, it's going to start at 40 AMU and not 30. And at some libraries that are commercial, they may start at a lower level, but you're not. And so if you've got ions in your library and not in your spectra, then you're reducing the actual library match, quality match that you're comparing to your library. So this helps to eliminate that from being a factor. We do have different types of library searches. You can do spectral, you can do retention time. Again, if we were doing a QTOF, we could do accurate mass, but we're not, so we're going to look at spectral searching. And since you can search multiple libraries, you can tell it to stop or continue depending upon how the library matches are found. we're going to tell it to search all the libraries. And then we also have the ability to perform exact mass. And again, we're not going to cover or talk about that at this point. Next is the target match tab, which we're not going to be doing any targeting. This is just normal data files and just doing data analysis on the data files and not anticipating any specific target compounds to be in these mixes. And so we're not going to cover this tab, again, due to time and trying to be very specific about the analysis of total unknowns that we're doing. Lastly, the blank subtraction tab. Normally you want to keep it checked, and what this will do is as it goes through the sample table, it will, every sample that is labeled a blank, it will subtract that blank from the that sample and then apply it to the next sample. So if you've got blank sample, blank sample, blank sample, and you have this checked, it should be taking and subtracting the blank from that blank sample and then subtracting it from the sample following it. And everything else we're going to leave as default settings. We're not going to change. The options you have at the bottom are to apply this method to all the samples or to a specific sample. Since we only have one sample in our sample table, we're just going to click it to apply to that one sample, and then we're going to close it. Now, to have our data analysis method applied to our sample data file, we're going to go to Method, to Analyze, and we're going to tell it either to analyze sample, or you can do an F6 function for a shortcut. So we're going to tell it to analyze the sample, and what that's going to do is do a peak detection, do a library search, and match everything and tell us what we've got. Notice now, and yours is probably in blue, I've changed mine to red so that you can see whichever is highlighted. But one of the neat things is that I like is that you can click on the different components in the components table. The peak will become highlighted, pointing to that peak in the tick. Now notice I have retention time and a compound name from the library on my peaks. Your system may not have that because mine has it turned on. So what you can do is put your cursor in your tick, right click on your mouse button, and come down to Properties. Now Properties will bring up a panel in which you can change your background color, your foreground, you can display grids or not display grids. You can change your fonts. In this instance, I'm using Roboto. I can change the font size. Remember, I was telling you my sizes are bigger than what the default setting is, I think of about 10. I can display my peak labels, and then I can determine what labels I want to display. So I've got retention time and compound name from the library search. For the best hit for the library search is the compound name. And notice what I don't have checked is allow overlap. If I check that and click apply, notice I'll have the hit that was missing from my last peak now show up, because in the software's mind, because this peak is so close to the edge of the screen, it would not be there completely. And so if I click allow overlap, it puts it there in the screen. If I take it off and apply, it takes it away. So allow overlap can help a lot of times, depending upon what your tick looks like, how busy it is, how many components are found, and how resolved they are from each other, or it can make it really busy. And you can change the different colors of the tick, and for the selected compounds, like I said, yours is probably blue. That's the default setting. I've changed mine to red so that it stands out a little bit more. And so just to show you, I can also add the cast number if I'd like to my list of labels. And so I'm going to apply that and click OK. And so now you can see from my list, I have the retention time, the compound name of the best hit, and the cast number. Because I allowed overlap, you can see that I've also got a labeling of a peak here at the 8.025 minutes section, whereas before it was not there either because it's overlapping this peak. And as I click on the different peaks, it highlights them in red, And as I click on the different ones, you can see that we have the extracted ion window here and the spectra here. This is in a head to tail configuration. If I put my cursor in the spectra and right click, I can take head to tail off, and now it's head to head comparison. If you'll notice, there are colored triangles in my spectra. And this relates to the color and the ion that is in the extracted ion. So again, what has happened here, I have the hexadodanic acid methyl ester, which is methylpalmitate, is a common name of one of the FAMEs that's in this mix. And we have extracted ions for 43, 143, 75, 87, and 74. Those are the extracted ions here, and then in the black is the TIC, the total ion chromatogram. Now, something that you can do if you'd like is come over here to view. Again, this is kind of controlling the view on your screen. As I can go to the view and I can click on EIC peak. What this is, and mine's in black. Don't know why mine always goes to black. It's supposed to be white. Yours is probably white. That's what it should be. And now what I've done, all this is a zoomed in portrait of what my ion peaks are. So the same ions have been extracted, but now it's zoomed in on these extracted ions, whereas my tick in this window is off scale. Something else I can do in the view window is I can ask for the molecular structure. If the library that you're using has molecular structure, it has ChemSpider or a mole file, a JPEG that has the chemical structure of the library hit assigned with it in the library, it will present it here. And so this is the structure of the methylpalmitate molecule that is in this peak. You can save this layout, you can change things. If I was doing QTOF, I could have exact mass, all types of things, and then save these layouts so that I can load it when I want to have it in my configuration. So this is a little busy, so I'm going to turn off my molecular structure, and I'm going to go ahead and turn off extracted ion peak chromatogram as well, so that I just have my chromatogram. One of the things to notice is that in my table, I have CAS numbers, which are underscored and highlighted. If your system is hooked up to the internet, this is actually linked to the webbook at NIST and will bring you to that. I am hooked on the internet, so I am going to go ahead and click on this, bring it up, and it takes me to NIST, to the webbook for dodecane, and gives me pertinent information, which is nice if you've got your system hooked up to the internet. Now, something that else I wanted to show you is that you can configure this table, and any table in MassHunter is configurable by putting your cursor in the table, right-clicking, and do an add remove column. When that happens, you can see this table pops up, and these are all the different choices in alphabetical order. You can break it down into sections based on your sample or component, base peak, different areas that it will help to separate out all the different components that you can make your table of. Everything on the left is everything that you could add to your table. Everything on the right is what is currently active in your table. And notice I have my CAS next to my compound names. If I wanted to move that, I could come over to the right side of the table, click on Move Down, and I could reposition it next to the library file on the other side of it. And if I do that, you can see now my CAS numbers are on the other side of my match factor. So you can put this in any type of configuration that you would like, save it to your layout, and so your tables will match what you want it to match as you go and use unknowns analysis. So this is our peak identification or peak integration results. Now we're going to go and do deconvolution. So we're going to go back into our method and edit it. But before we do, notice that components, it found 11 components in this. So in other words, when it did the integration parameters, which unknowns uses two different integration, it uses an Agile or an Agile 2. These are both parameterless integrators that are algorithms that look and seek out your baseline and determine when your peaks start and stop. Very similar to what you're using when you do integrator events in ChemStation, but in this instance, there are parameterless integrators in events. There aren't any specific events that you can change and adjust, except as you saw earlier, we could filter by area or height abundance, but there's no skin slope sensitivity or baseline reject or any settings like that there is in ChemStation. These are algorithms that are parameterless. It defaults to the Agile 2 algorithm, which is actually a very good algorithm. I use it the majority of the time. It's very reproducible. It's a very good algorithm to use for integrations of a very busy tick where you've got a lot of coelutions, a very tight resolution between compounds. It will integrate them very well and very reproducibly. And so what we're going to do now, based on this Agile 2 integration, is we're going to change it in our method editor, and we're going to change our integration to deconvolution. If we go to Method Edit and go to the Peak Identification File tab, we have tick analysis. We're going to drop that down and change it to deconvolution. Now, when we do, the deconvolution tab that we skipped earlier, we're going to go to. And I'm going to give a very brief description of what the retention time size factor means in this window. And you see we have default of 25, 50, 100, and 200. These are scan sizes that are dimensionless. In other words, it's not in scans per second or AMUs or in minutes or anything like that. It's just on the size of the number itself. So in other words, in this instance, 25 would be a smaller window that it's pulling out data than 50 would be, than 100 would be, than 200. And so depending upon the component peak widths, your peak shapes, a narrower peak shape would be most likely to be read in a 25 size factor as opposed to a medium in a 50 to 100 to 200. And so by scanning these different window size factors, as deconvolution is going across and scanning across the peak, it's looking for these different component sizes. And remember, pulling out the different extracted ions based on peak shape, this size factor, and the retention time of the extracted ions, and then building a spectra accordingly. The nice thing about unknowns analysis is that it does all four of these different size factors at the same time, and so it doesn't cost you anything. Whereas when you do deconvolution in qualitative analysis, as I mentioned earlier that you could, in qualitative analysis, it only does one size factor at a time. And I think everybody realizes you have varying peak widths and sizes of your peak shapes all throughout your chromatogram based on a multitude of parameters, whether it's concentration, reactivity with the stationary phase, whether they're early eluders, late eluders, all different types of components. And so these four are really good to use starting out and continually through your run, but it's something you can play with once you've mastered and have a better understanding of unknowns analysis. The extraction windows of 0.3 and 0.7 are default. I would leave them at default. Our delta units for our mass to charge is AMU. We have parts per million, which is for QTOF. We're not going to use that. We can also use a specific peak shape, which we're going to leave turned off right now. And our minimum number of ions and our minimum number of ion peak shapes to store, we're going to leave at default as well. Everything else we're going to leave the same on our other tabs. I do like to go to the library search tab just to make sure nothing's changed, that my library is there. Now I'm going to click on apply to selected sample. And you can see my components and my hits are now blank because before we had done peak integration. And so it's cleared out those fields, and now it's going to do deconvolution. And so we're going to close this window, go back to Analyze, and either do Analyze Sample or F6. And so it's doing the peak detection, but doing deconvolution. And now notice one of the big things that should come out of this is that our components list, if you remember, we had 11. Our hits were at 6, whereas now we're at 4. Based on the different parameters, it has found the 4 components in our system. And we have a connecting, as we click on the components table, our spectra for each one. This is very well resolved, very clean baseline spectra. And so we really don't have the need for deconvolution, but we do have the ability to be able to use it. And you can see that our library matches are better than they were before on just doing peak analysis, because it is going through and cleaning up the spectra. And I'm going to go ahead and go back to head to tail, because that's what I prefer. I like looking at the head to tail. I feel like I have a better comparison of the spectra. And then doing deconvolution, we can look at the extracted spectrum. Because we have such good peak widths and good sharp peaks and a clean baseline, there's really very little deconvolution that is occurring in our tick. Okay, next what I'd like to show you is, remember when we were setting up our method, I said you could use several different parameters as filters when you're looking at your data, one of those being signal to noise, another one being the library match minimum. So notice on our deconvolution, which should be digging out things in our baselines and things like that, actually has fewer hits. It has 4 hits, whereas our peak integration actually, I believe, had 6. And we know the components have increased, so it actually detected or integrated 61 components, but notice only 4 hits. 4 hits is based upon compounds matching our minimum detection match in our library quality match. With a quality match of 70, these are the only components that were detected that fell and met that criteria of 70 or greater. And you can see they're 99.1, 0.5, 99.5, 97. We can see visible deflections in our baseline. And in fact, we know how to do this. We can right click, drag, and move it up. And we actually can see some deflections in here. The question is, why aren't these integrated? And the answer is because we did not have a low enough library match score to be able to pull these up. If we would like to, we can go to Method, go to Edit, and go to the Components tab, and where it says 70, let's put in 50, and let's apply it to the selected sample. Let's close. Now notice our components went away, our spectra went away, my integration parameter numbers went away, but notice components are still here at 61. They did not clear out that table. Well, it didn't, because we're not asking it to deconvolute the tick. We're asking it just to research the libraries. And so what we can do when we come to analyze, we could tell it to analyze sample, and it wouldn't hurt. It would just take more time. With one sample, the time is appreciable. But when you have 30 or 40 or 50 samples and you want a library search, reanalyzing the whole batch or that number of samples does take more time. So in this instance, we don't want to deconvolute our data file for integration. We just want to do a library search match. And so now what it's going to do is take what was deconvoluted earlier, and now using those library parameters, go and match the components. Now notice we had 61 components, 4 hits, and now we have 10 hits. And you can see what I was saying, to where when you allow overlap, if you've got a lot of compounds there, it can get kind of ugly. So just to kind of clean this up a little bit, I'm going to go to Properties, and I'm going to tell it to not allow overlap. And that makes it look a little neater. Now remember, we can still zoom into our baseline, and you can see that where I have my cursor at 8.5 minutes, you can see that that gets highlighted at 8.5 minutes. The black is the tick, the red is the extracted ion that has been deconvoluted. You can see now that what things that did not have integration and possible library matches to them now do have a retention time, a library name, and a CAS number. Now granted, this at 8.5 is only a 61 quality match. And again, you're not going to call that a positive based on this match, unless obviously you've got standards and this isn't a matrix and things like that. But it would be pulling this out more if this was a better quality match, because that's what the deconvolution algorithm does. However, what it can do a lot of times is give you an idea of the classification or the functional groups on a specific compound that can help lead you to doing additional research and better identification of the components. Now notice there are still, and I'm going to right click and drag, there are still components that do not have in this baseline anything underneath them as far as integration. And that's because a match score of 50 was not going to give any type of quality match here. So this does not meet that minimum of 50 library quality match. Also notice there's a data point here, a data point here, and a data point here. If you zoom in, that's only 3 data points across the peak to get spectra. So there's not a lot of spectra here. If you look over here, you've got a data point here, a data point here, a scan point here, and another scan point here for data. So one of the things that you need to do and look at when you're using unknowns analysis and specifically using deconvolution is to look at your scans under your peak. And probably for most of you, you're probably getting about 6 to 8 scans under your peak. And what you want to do is get about 10 scans under the peak for qualitative analysis. So most of you are probably acquiring data and your scan speed is set to n equals 2. And for using deconvolution and unknowns analysis, you'll get better spectral quality, better spectral matching. And even if you're not using deconvolution, you get more data points. And if you would change your scan range down to n equals 1 as opposed to n equals 2. Now, n equals 0, you're going to get more than likely, unless you're doing very, very fast chromatography, you're going to get way too many data points. But an n equals 1 is going to give you a better average of scans under your peak of anywhere from 10 to 12 probably. And if you look in the qualitative analysis, it will show you the number of scans. And if you highlight your peak in ChemStation, it'll tell you the number of scans underneath that peak. And for the best quality matching, and especially for deconvolution, you want to get at least 10 to 12 scans under your peak. Okay, remember, if we want to back out of this, we just right-click menu and go to auto scale. We've got these hits based on our library match. So we've got a total of 10 hits. What I want you to do, just to kind of explain how that window size factor works, is I'm going to move my table over a little bit. And in fact, I'm going to just make my table float here to put it in the middle of the screen. So I right-clicked on the menu button, told it to float. Notice that in my table, I have window size factor. So if you do not have the window size factor in your table, I want you to right-click in the table, go to Add Remove Columns, come over to the left side, this is in alphabetical order, and come all the way down to the bottom, and at W, you're going to see window size factor. Okay, and I want you to bring it over here to what's going to display in your table. Then I want you to move it up about 6 or 7 spaces near the best hit column. Once you do that, what we're going to do is, I'm going to move this over just a little bit, is up here at the top, we have different designations. We have look at all the hits, look at just targets and non-targets, which that's if you're quantitating and you have known compounds in your data file, you can assign the target listing. It'll know what that is. We have a hit, which is specifically something that has been found by the library to match your library requirements. In this instance, we have 10 hits. We have non-hits, which non-hits are those other 61, or in this case, other 51 components, which don't have a library map. So we have 51 non-hits and 10 hits. And so what this area of topics is doing up here is helping to filter our components table. So if you've got a very, very busy tick with a lot of different components in it, if you're doing toxicology, and so you've got a lot of matrix peaks and stuff in there, you want to filter out your components table and not have 100 different compounds in it that aren't relevant to what you're looking for. And so this allows you to be able to do better filtering. Now, notice we have hits highlighted, but then we have the best hit. If we untag best hit, now notice we have extra hits for the 5.277 for dodecane. We'll take that at first. And notice the match factor is changing depending upon where the deconvolution algorithm is going over and scanning that peak. And so it's using a Windows size factor of 25. That generates a match factor of 98, 100 of 99, 50 of 99.0, 200 of a 99.1. So as it's going through its retention time and scanning, it's using those different window size factors. What best hit does is give us the best quality match based on the best size factor match for our library. And so you notice we've got multiple hits based on the Windows size factor, and it changes throughout the peak and based on the peak width of our individual compound. These are fairly high responders in 10 to the 6th range, fairly wide peaks for capillary. Not everything works the best. In this instance, we've got, let's see here, we've got 99.1. So it looks like 100 is the best hit for dodecane when it comes to a Windows size factor. And when we go to biphenyl, it looks like 99.5. Looks like 100 is best for it. If we go to the bichloral, the 1,1-biphenyl 4-chloro, let's see, we've got 99.5 at 100, 99.5 at 200. So one of those two are going to be the best hit. And we can go on down and let's look at the methylpalmitate, which is a little bit smaller of a peak. So 95 at 200 is giving us the best hit. And so all these check marks are showing us the best hit for these different compounds. And so if I click here, right click and unfloat it, and I recheck best hit, now our hits are filtered, and the best quality match for this window size factor for this component was 200. For the biphenyl, it was 100 best quality match, and so forth and so on, going down the list. A way to be able to filter and determine what is the best quality match for your library hit. Now, if for some reason you have multiple libraries and your SOPs dictate that you need to use your library match as the positive identification for a component, what you can do is right-click on the component, get a right-click menu in your table, and go Show Alternate Hits. Now, what this does is it's showing the alternate hits that happen to be in the NIST library. Remember, we told it we only wanted to see one hit as our max number of hits. And so now it's saying, all right, where you're using the NIST library, we have multiple spectra entered for dodecane. And so anything that's similar to dodecane and similar to our scoring, it's giving us the top hits. And so we've got dodecane as the first 4 hits, and then we've got some dodecane derivatives, hexadecane, some other fragments that are off of structurally similar to dodecane, and which we would expect because straight chain hydrocarbons, their spectra is very isobaric for a lot of the compounds. They don't generate a lot of large fragments and small fragments that are the 14 AMU apart from each other. And usually you don't get a molecular ion a lot of times, especially on the bigger alkanes. So it's not unusual to see that you've got multiple hits for the same and or different compounds in the 90s. So what we could do if we said, okay, this isn't dodecane, or this is dodecane, but it's founded in the NIST library, but it didn't find it as the best hit in my library, but let's say it was in the 90s. We could actually click on it, and what I'm going to do is I'm going to say this is hexadecane, just to show you that it changes. And we're going to say, no, it's not dodecane, it's really hexadecane, and you hit set best hit. You're going to close this, And so now where it was dodecane, we have it as hexadecane. Now, some QC people may not like that factor, but it is something that you can do as far as change it, especially if you want it to be in your library and not in another commercial library that you might be searching at the same time. And you have the possibility as well, let's say, okay, we don't want anything under 90 in our components table. We can either go back and research, set our component identification from 50 to 70, or we could come over here and say, okay, we've got this 3,4,5 trimethyl something or other here, and it's at 55. I don't want it in my table. I can right click and I can delete the component. Again, that may bother some people. It's still there. It's not that you've deleted it totally from the data file. It is just in this batch of unknowns analysis that we have affected this change. And so if we wanted to do that, we could hold our control button down and click on all the components that are below 90, right click, and tell it to delete those components. Or the same thing would occur if you went to the method and told it to change your library match quality to 70. You're doing the same thing, it's just you're doing it manually when you're using the keypad and using the control button. Next, what I'm going to do is show you a more complicated file. You're not going to be able to follow along with me because it's going to be on a toxicology sample of standards, but I'm going to show you how deconvolution can really help you in finding peaks that are covered up. And I'm going to show you how to create a library in just a few minutes. I'm going to show you that with the tox sample that I'm going to load. And then in part 2 of the video series, we will be covering forensic case samples and loading several forensic case samples that you'll be able to follow along and see how deconvolution can help you in screening and identifying components in your various case samples. Let's go and add a sample to our batch file called training. So we're going to go to File, go to Add Sample. Now, this is an example of this data file that I'm going to use is not in this directory. And you don't have this data file. I apologize, but you don't have it. But I do want to use it to demonstrate what it can do for you. So I'm going to go to MassHunter, go to Data. It is in my Forensics Data folder, and it is this tox sample.d. I'm going to add that to my batch table. That's highlighted, and I'm going to click OK, and now it shows up in my batch table. Now, I'm going to do this a little faster because we've gone through the process. So what I'm going to do is click on the sample, and I will go through the method parameters again. I'm going to do peak integration first, the tick analysis. I'm not going to change anything here. I'm not going to do the deconvolution tab because I'm not using it yet. I am going to change and make sure that I use the NIST library. Then I think I will also use Swig drug as well. So I'm going to double click on the NIST and then add a library, use Swig drug. Okay, so it will search the NIST library first and then the Swig drug library. And then whichever hits that are present gives me the highest score, is that's what will be displayed. I'm not going to change anything on this tab. My compound match factor, I'm going to put that back up to 70. I'm not going to change anything anywhere else. The blank subtraction, not going to have on because I don't have any blanks in my system. I'm going to apply this to the sample that I have highlighted, close it, and you can see this is a much busier chromatogram. So now what I'm going to do is go up to Analyze, Analyze Sample, doing, remember, the peak integration or tick analysis, not doing deconvolution. Then it's doing the library searching of those two libraries. And then it found 75 components, 49 hits. So 49 components out of the overall what was detected were identified based on my signal to noise and my threshold library searching at 70. There's all kinds of different components in here. You can see if I click on, I've got phentermine in here, which I can scroll down. I've got meperidine, methadone. Now, what I want to do is I want to show you between 3.5 and 3.7. I'm going to zoom in. There's oxycodone at 3.7 minutes, so I'm going to scroll down and look at my oxy. And so I've got oxycodone. So this is just peak integration, seeing oxycodone, giving me the CAS, because remember, that's what we had checked before. This is our deconvoluted data, our library matched data, our raw data, okay, is what's in the system. Okay, and so it's giving me a 95.4 quality match on my oxycodone. 75 components, and 49 of those matched a 70 or greater library score based on NIST or SWIG drug. SWIG drug found 1, 2, 3 different components in SWIG drug as opposed to NIST, which is fine. I mean, again, that's why you use multiple libraries. So now what I'm going to do is go to the method. I'm going to edit it again. This time I'm going to change it from tick analysis to deconvolution. And I'm going to go to the deconvolution tab. I'm going to keep everything the same here. I'm not going to change anything. I'm going to recheck my libraries just to make sure they're there. I'm going to apply this to the sample. I'm not just library searching, I'm also integrating it differently. So my components and my hits are gone. Now I'm going to go up to analyze, tell it to analyze sample. So it's going to deconvolute it. It's going to do a library search and target match, which is we're not doing any target matching, and blank subtracting, which we're not doing, which when it gets to those areas, it goes. I have 1,087 components. So deconvolution was digging in my baseline and seeing where I had some coelution coming out. And instead of, I think it was 49 hits, we now have 112 using deconvolution. Remember, we kept quality match of our library at 70. Just using deconvolution, it found a little bit more than twice, actually, than the 49 that we had before just doing peak integration. And I'm going to purposely zoom in between that 3.5 and 3.7, look specifically at my oxycodone. We all should know how to do this now. I'm right-clicking and dragging on my y-axis, and I'm going to left-click and drag on my x-axis. Notice if we now go in our table and we highlight, was it 3.7 oxycodone? Well, it just rescaled everything for the oxy. The oxy is in red, and then the tick is in black. Well, notice there's another peak under my oxycodone that's in green. And if I click on what that peak is to make it red, and now zoom back in, it's cannabinol with a 77 quality match. It is coming out underneath the oxycodone. This is where you can see the power of the deconvolution, because under the oxycodone, you have a match for cannabinol at a 77, which is not great. And again, it's whether or not you want to run a sample and match retention times and everything else and extract whether it's worth it all or not. But maybe this isn't cannabinol, maybe it's fentanyl or one of the fentanyl analogs under quinine or something like that that you would need to see. And so this is our deconvoluted spectra. This is our library spectra. This is our raw spectra. Remember, the majority of this peak is oxy. So deconvolution is pulling the cannabinol ions out of this with the same retention time and peak shape to build the spectral table for cannabinol away from the oxycodone. This can really benefit you and really speed up the process for screening your samples for known components and target compounds that you're interested in. It's not to take away you making the decision of what is the best hit, whether it's a good quality hit, whether it matches the library. And this does a much faster and better job of doing deconvolution via the algorithm, as opposed to you scanning the front of the peak, scanning the back of the peak, and doing background subtractions, and maybe even missing the peak. Hopefully, at this point in the video, I've gotten your attention with some of the features and abilities of unknowns analysis. To bring this video to a close, the last thing I'm going to show you how to generate a library in unknowns analysis. It takes approximately just a few minutes to generate, and that will wrap up this part 1 video and hopefully take you to video number 2, which will be a demonstration of forensic files and forensic cases and how deconvolution and unknowns analysis can really help you and your laboratory's data analysis become more efficient. So with that said, let's move on to creating a library. And we're going to use our toxstandard.d library file and scroll up to the very top using the scroll bar of our components table. And I'm going to click on a few various components in this. So I'm going to click on amphetamine with my left mouse button. And then what I'm going to do is hold on the control button on my keyboard, and clicking on amphetamine, I'm going to go to the scroll bar with my cursor and I'm going to pull down, and I've clicked on amphetamine as an early eluter, and I'm just going to start clicking on some more compounds that elute a little bit closer together and are just closer in the table. So I'm going to click on meperidine, on phencyclidine, and I've got some down here at the bottom at 3 minutes, methadone. And again, I'm going to use that scroll bar on the right side of my components table to move. And I'm going to go to cocaine. I'll do some profadin, oxazepam. Let's do codeine, diazepam, hydrocodone, do some oxy. We want to add cannabinol. It's not a real good match at 77. Timazepam, fluornartazepam, heroin, some strychnine, some vermipamil, prazolam, and clonazepam. And there's some nitrazepam. So we've got all of these compounds highlighted by holding our control button down. Now what I'm going to do is right-click on one of those compounds, and I'm going to tell it to export. Now on the screen we have where it exports, and we can select all compound hits that are in our components table or just our selected compounds, which is what we're going to do. And we can export it to a library. We can also export, as you've seen, to a CSV file and to a quantitative analysis method, which is great for creating a quant method from unknowns. It adds your targets just as easily and quickly as we're adding these entries into a library. Now, you can also add a prefix to the library. In other words, this could be base extracts, acid extracts, it could be benzodiazepines, it could be fentanyl analog. However you want to name it, I'm going to keep the prefix as unknown. And we can also bring in our retention times that are with our compound. So I'm going to click on OK, and it's going to open up library editor software, and I'm going to click on create a new library. And when I do, it's going to bring me to my library directory, which in my instance is on my C drive under the library. I'm going to call this unknowns_test, and I'm going to save it. And when I do, it imports this library. All of the hits that I selected in my components table have now been brought over into the library with their spectra, with all the relative information from the library that I used to identify these compounds. So in this instance, it was NIST and SWIG drug, and depending upon the library, it also brought over the structure, if that was part of the library entry in the library that I used. Brought in my retention times, CAS numbers, formulas, my mol files or JPEG files, depending upon my images. This is a table in MassHunter, and so I can right-click in the table, go to columns, and I can customize somewhat my table in the library editor. Okay, so what's on the left is still what's available to bring over to my table that is currently on the right and active. So literally, again, it took longer for me to explain it than it did for me to actually generate and create the library. So I'm going to save this library with my unknown test, our mslibrary.xml, and this is an editable library. We can add to it, we can delete compounds, we can change entries in the compounds. I'm going to save it, close it, and then I'm going to go back up to my data analysis method in unknowns analysis, and I'm going to specifically go to the library search tab, and I'm going to remove my NIST and my SWIG drug library, and I'm going to add my unknowns library underscore test, add that to my tab, make sure I've got everything is the same, running deconvolution, my peak detection, and everything's the same. I'm going to apply it to this sample. Notice that my components are still at 1087 because I'm not doing any integration. I just want to do a library search. And so I'm going to close my data editor panel, go up to Analyze, and just click on Library Search. It's going to save me a little bit of time as it's searching the library, brings up my hits, and so I had 19 entries into my library because that's the only drugs it's going to find or what my entries are because I just limited it to that new library. And something that you won't see in ChemStation is I have 100% quality match because it's cleaned, deconvoluted library spectra of the drugs. It will give me 100%, whereas you can create a library in ChemStation and you'll get 95, 97, 98. I really haven't seen too many 99s, and I have not seen 100% using ChemStation. You can see the library file that we use, window size factors, and what was giving us the best quality matches. This is a very easy way to generate a library and also generate a quant method from a data file of standards. I hope this video has been informative to you, and I hope you're interested to go to video number 2 and watch it. Thank you very much for your time.
Thank you so much, Kirk. While we would typically proceed into our Q&A now, we are already a few minutes over the bottom of the hour, and we'll proceed with closing the event. In the second part of today's event, we'll have more time at the conclusion to reply to any remaining questions, as well as what comes through the day of the presentation. Before we do conclude, please join me in thanking our presenter, Kirk Lockett, as well as our expert panelists, Matt Curtis and Rachel Ciotti, for monitoring and replying to your many questions. If you do have any additional questions, that Q&A engagement tool will still be available in the on-demand console. As mentioned above, those will either be replied to during next week's continuation of the topic or offline via email. If you have any additional feedback, comments, or topics of interest that you would like to see in our future webinars, please feel free to fill out the survey if you haven't taken the opportunity. And this is just in our engagement toolbar, which I have also brought to the center of your screen now. As mentioned earlier, we will have the second part of today's session next week, featuring Kirk Lockett. And this is the URL where you can check out and register for that upcoming event, as well as view the on-demand recordings which were previously presented. One last reminder, the recording itself will be sent out in approximately 24 hours. You can access this using your audience link, which you used today, or refer to the information provided in our follow-up emails. Thank you all once again for attending today's webcast. And on behalf of Agilent Technologies, we wish you a great day.